And so we begin with chapter 2, which is titled representing space non-right angled trigonometry and volumes. So in the first chapter, we did some trigonometry. In particular, we did SOHCAHTOA, which is an acronym for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. But hypotenuse, the fact that you have an hypotenuse means you're dealing with a right-angled triangle. Otherwise, we don't have a hypotenuse. So what happens if the triangle is not right-angled? Well, that's what this section is all about. So for right-angled triangles, there were two mathematical ideas that were appropriate. SOHCAHTOA, sine, cosine, and tangent, and the Pythagorean theorem, a squared plus b squared is equal to c squared, where c is the hypotenuse. Neither of those can be used for a non-right-angled triangle. So for a non-right-angled triangle, if we call the 3 points, the 3 vertices of the triangle, capital A, capital B, and capital C, the book tends to make a distinction between the vertex and the angle. So capital A, and then what they'll do here is they'll put an A with a little hat on top to represent the angle. And similarly, this here, B hat is the angle, C hat is the angle. I'm not used to that. I just call the angle A, the angle B, the angle C. So I make a distinction between the angle and the side by using lowercase letters for the side. You'll notice that lowercase a, side A, has to be opposite angle A, and lowercase b, side B, has to be opposite angle B, and lowercase c has to be opposite side angle C. Of course, with C, upper C and a lower C look the same. It's just you have to be very obvious when you write it which one it is by the size. So my capital C's I'll make bigger, my lowercase c's I'll tend to make very small, which could be one reason why the book likes to use these hats to be even better. I'll do my best. I make no promises. I might use hats, I might not. So just be aware, capital is angles and lowercase is sides. And there's two properties, two mathematical ideas that we will use for non-right angled triangles, and that is the law of sines and the law of cosines. Okay, and section 2.1, which is what we are doing today in this lecture, section 2.1 is on the law of sines. Is it also on the law of cosines? Yes, it's on both. So section 2.1, that's what we're doing today. The trigonometry of non-right triangles. I'm actually going to move this up here and then move that a little lower. So section 2.1, trigonometry, excuse me, of non-right angle triangles, in particular, the law of sines and the law of cosines. So let's start with the law of sines. What is the law of sines? The law of sines is very, very, very simple, very important. We're not proving it. The proof is a little complicated. But it says if you take the sine, that's why it's called the law of sines. If you take the sine of angle A and divide it by the length of side A, and you do the same thing for angle B and side B, and the same thing for angle C and side C, these are all equal. Sine of A over A equals sine of B over B equals sine of C over C. And sometimes it might be useful to write it the other way. A over sine A equals B over sine of angle B equals C over sine of angle C. Either way works. I tend to use the version that has a thing that I'm looking for on top. So if I'm looking for an angle, I'll use the first version where the angles are on top. And if I'm looking for a side, I'll use the second version where the sides are on top. It doesn't really matter. Either way works. It's just personal choice. The math is a little bit easier if the thing that you're looking for is on top. So let's demonstrate this math with some examples. So example number 1. You have a triangle, and I will try to recreate the triangle that's in the book, but it actually doesn't really matter. So you're given a bunch of stuff. Okay, it says triangle QRS, where Q is down here, R is up here, and S is here. It tells me that QR, capital Q, capital R, is equal to 15 meters. What is capital Q, capital R? It is the side that connects vertices Q and R. So this one here is 15 meters. It tells me that SR is 6.5 meters. So SR, the side that connects vertex S, vertex R is the top, 6.5 meters. And it tells me that S hat is 125 degrees. What is S hat? It is the angle at vertex S. So this is here is 125 degrees. Notice, and it wants Q hat, by the way. This is what it's looking for. What is Q hat? So first notice that this may be a right triangle just because I didn't, well, actually it can't be a right triangle because we have a 125 degree angle. And we know that in a right triangle, one angle is 90. So the other two have to add to 90. So nothing can be 125. So this is certainly not a right angle triangle. You cannot use SOHCAHTOA. You cannot use the Pythagorean theorem. What can you use? The law of sines. Now, if you look in your formula book, just so you know, the law of sines is given, or at least one of the two versions is, as is the law of cosines, by the way, when we get to it. It's good to remember, but it is there. So when are you allowed to use, or when should you use the law of sines? What is a good mental concept to keep in mind for when the law of sines is appropriate? You need an angle side pair. That means an angle on the side opposite it, and something else. That something else could be an angle or a side, but you certainly need an angle side pair if you want to use the law of sines. Do we have one? And the answer is yes. We see that angle S and the side opposite angle S, we know we have an angle side pair and something else. Because we have an angle side pair and something else, we are allowed to use the law of sines. What are we looking for? We're looking for an angle, so we'll use the first version. Sine of angle S, I guess we'll put S hat. Try to match the book, even though I'll probably forget eventually. But sine of S hat over side opposite, which is QR, equals sine of Q hat over the side opposite, which is SR. In other words, sine of 125 degrees over 15. I'm suppressing the units, but I'll put them back in at the end if necessary, equals sine of Q hat, which I don't know, over the side opposite Q hat, which is 6.5. Again, units are suppressed. So now we take out a calculator. This can usually only be done with a calculator unless the angles are one of the nice angles. You need a calculator to use the law of sines or the law of cosines. So make sure your calculator's in degree mode. Sine of 125 divided by 15 times 6.5. So what we get is that sine of q hat is approximately 0.355. Now, just so you know, obviously my calculator does not say 0.355. It says 0.3549 and whatever those numbers are. I can't read them backwards. But even though I only write down on my page 0.355, any subsequent calculations, I make sure to use all decimals. So you have to use the complete number so that you have maximum accuracy. Now, we know what sine of q hat is, but the goal is to find q hat. How do I get from knowing the sine of q hat to knowing q hat? So for this one, I do the arc sine. The arc sine removes the sine. It's the inverse. So arc sine of sine canceled each other. Arc sine of q hat, which is just q hat, equals arc sine of 0.355. Again, make sure you use all decimals, even though you're only writing 0.355. And when I do arc sine of answer on my calculator, I get that q hat is approximately 20.8. 20.8 what? 20.8 degrees. We just found an angle. If you don't write that, no units, it's wrong. So know what you're looking for. Sometimes you're looking for an angle. Sometimes you're looking for a side. Always be aware of what you're looking for to make sure that you use the right units. Let's do another example. It says a ship S is on a bearing of 120 degrees from port A. Bearing. So you're going to see these a lot. Bearings. What exactly is a bearing? Well, here's port A. We always do, when it comes to bearings, is we always draw a line straight north. Okay, bearings are always in relationship or related to a direct north starting point. So when we have a bearing of 120 degrees from port A, that means you start north and then you tilt clockwise like a clock. You tilt to the right 120 degrees, which means you're going roughly in this direction. This here is a 120 degree bearing. Okay, and so we have a bearing of 120 degrees from port A and 42 degrees from port B. So here's the ship. Here's the ship. They called it ship S. There's the ship. So to have a 42 degree bearing from port B means that we're going to tilt 42 degrees, which means B must be down here somewhere. So that when I draw my north looking bearing, I tilt 42 degrees. Actually, it's 42 degrees to the east. You always tilt to the east clockwise. Okay, so I have my 120 degree bearing from port A, and I have my 42 degree bearing from port B. The distance between ports A and B is 15.2 miles. So we also have the distance from port A and port B. This guy here is 15.2 miles. Find the distance between the ship and each port. So we're looking for this, we'll call it X. We're looking for this, we'll call it Y. What is X and what is Y? Well, we have a triangle here. These three lines that I drew form a triangle. Is it a right triangle? No. I mean, it might kind of look like a right triangle, but 120 and 42 doesn't quite work to make a right triangle. And even if it was, we're not given that it's a right triangle. Unless you can prove it, don't assume it. Which means all we have is either the law of sines or the law of cosines. But to use the law of sines and the law of cosines, sorry, not the law of cosines, to use the law of sines, because we haven't yet learned the law of cosines, you need an angle side pair. Well, I only have one side. So if I'm going to use an angle side pair, I got to figure out this angle right there. Otherwise, I can't use the law of sines. So how do I find angle S hat? Well, let's take a look. I have 42 degrees in the bottom. That 42 degrees is inside the triangle. Great. Now the 120 degrees is not inside the triangle, so it's not one of my three angles, but the other part is 60 degrees right there. 120 and 60 is 180. We know a straight line makes a 180 degree angle. It's half of the circle. So now that I have 60 and 42, now I can compute the third angle of the triangle as 78 degrees. Once I have the third angle of the triangle, now I do have an angle side pair. Notice I'm looking for a side here. So I'm going to have the side lengths on top, 15.2 over sine of 78 degrees is equal to what I'm currently calling x over its angle, over its sine of its angle, which is sine of 42 degrees, and also equal to what I'm currently calling y over the sine of its opposite angle. So now that I have my equation, now I just, my equation is technically, now I just calculate 15.2 divided by sine of 78. If I multiply that by sine of 42 degrees, I get that x is 10.4. What are my units? Miles. And if I go back to the first one and multiply it by sine of 60 degrees, I get that y is approximately 13.5 miles. Both 2, 3 significant figures. So with that under our belt, let's go ahead and do exercise 2A. So exercise 2A. This is a small one, only 3 questions. Again, as always, you should be trying them yourself before you see my answer, and then writing your work and my work in your notebook. Okay, question 1. Find the unknown angle for each triangle ABC and give your answers correct to 3 significant figures. So we have a triangle. We're not told that it's a right triangle, so we don't assume it's a right triangle. Vertex A on top, vertex B bottom left, vertex C, this number bottom right, side A opposite angle, opposite vertex A, side B opposite vertex B, and side C opposite vertex C. Okay, and so we're going to use the same picture for all 3 of these. So the first one says side A equals 12.5 centimeters, side B equals 15.4 centimeters, and angle B hat equals 68 degrees. And it says find the, and then it says find A hat. Find A hat. Now you're more than welcome, of course. I mean, presumably you're doing this yourself. So make a different triangle for each one. I'm just going to kind of check off what I have for this example. I have 3 of those. I'm looking for the 4th. So I have an angle side pair, looking for another angle side pair. So this is certainly a law of sine scenario. So since I'm looking for an angle, angles go on top. So sine of B hat over side B, unit suppressed, equals sine of A hat over side A, units suppressed. So sine of 68 degrees divided by 15.4, get the answer, multiply by 12.5. So sine of A hat is approximately 0.753. And therefore A hat is approximately the inverse sine, or sine inverse or arc sine of 0.753, which is approximately, to 3 significant figures, 48.8 degrees. Question B, same picture. This one, I'm given B is equal to 42.8 centimeters, C is equal to 30.6 centimeters, and C hat is equal to 41 degrees. And the question says, find B hat. I don't even need the picture. The beautiful thing about labeling them as ABC, ABC is I can immediately see pairs. C and C hat is a pair, B and B hat is a pair. Law of sines. So angles on top, because I'm looking for an angle. So sine of 41 degrees over 30.6 units suppressed equals sine of currently unknown B hat over 42.8, again, units suppressed. Sine of 41 degrees divided by 30.6, multiply that by 42.8, take the inverse sine, and we get, therefore, that B hat is approximately 66.6 degrees. And part C, A is equal to 7.2 meters, C is equal to 5.1 meters, A hat is equal to 70 degrees. And the question is, what is C hat? Again, AACC, we have angle side pair. So we can use the law of sines. We're looking for an angle. So angles on top, sine 70 degrees over 7.2 units suppressed equals sine of C hat over 5.1 units suppressed. So sine of 70 degrees divided by 7.2, multiply 5.1, take the inverse sine, and we get C hat is approximately 41.7 degrees. You see, once you get the hang of it, very, very fast. Question number 2. It says in triangle ABC, so I'm going to draw a random triangle, A, B, C. AC equals 8 centimeters. AC is the side that connects A and C. Units are centimeters, so you know it's the length. C hat is equal to 101 degrees. Certainly not a right triangle. B hat is 32 degrees. It says find the lengths of AB and BC. So we're looking for AB and we're looking for BC, which I'm just going to call X and Y. Do we have an angle side pair? Yes, we do. But more importantly, we have 2 angles. Not more importantly, but just we happen to have 2 angles. Because we have 2 angles, we automatically get the third angle. The third angle comes along for free because the 3 angles of a flat right triangle have to add to 180 degrees. So 101 plus 32 is 133, which makes the third angle 47 degrees. Now that I know that, if I want to find X, which is a length, I'm going to have X on top, so sides on top. So 8 over sine of 32 degrees equals X over sine of 101 degrees, and it's equal to Y over sine of 47 degrees. So 8 divided by sine of 32 degrees times sine of 101 degrees. I get X is approximately 14.8. One of my units, centimeters. And I get Y is approximately 11.0, again, centimeters. Notice, by the way, that the longest side is opposite the biggest angle. The medium side is opposite the medium angle, and the smaller side is opposite the smallest angle. That will always be true. So it's a good way of checking your work. And more importantly, sometimes, as we're going to see, hopefully, there might be more than one possible answer to a problem, and you can eliminate one answer by noticing that the biggest and the biggest and the middle and the middle and the smallest do not necessarily align, which is a way of knowing that it's not a valid solution. So now we do question 3. It says a ship is sailing due north. Okay, fine. No picture, so I'll make my own. Here's the ship, and it is sailing due north. Let's do a better. Okay, due north. The captain sees a lighthouse 12. So here's the ship right now. And the captain sees a lighthouse 12 kilometers away on a bearing of 36 degrees. 36 degrees is you draw straight north, which we already had. You tilt to the east 36 degrees, so it's about this way. And there it is. Here is the lighthouse. We'll call it L for lighthouse. And this distance is 12 kilometers. And the bearing is 36 degrees. Later, later, which means that we are now somewhere else along this north path because we have been we have been traveling. So later, the captain observes the bearing of the lighthouse is 125 degrees. So now, now we're here. No, where would we be? About here. And now the bearing to the same lighthouse is 125 degrees. How far did the ship travel between these two observations? So we're looking for this length right here. How far did it travel? So do we have an angle side pair? Well, first of all, it's not a right triangle, or at least I don't know that it's a right triangle. And I need an angle side pair if I'm going to use the law of sines. I do not have one, but can I infer? Well, we have 125 degrees, which makes this one here 55 degrees. And now that I have those two, I know that this is going to be 89 degrees. Almost a right triangle, but not quite. And now I have an angle side pair. So I have, I'm looking for a length, so sides on top. 12 over sine of 55 degrees equals x over sine of 89 degrees. 12 divided by sine 55 times sine 89 gives me that x is approximately 14.6, and one of my units, kilometers, and we are done. So section 12A is complete. Now, we have another example, which means we're going to do a new example that still uses the law of sines because I haven't yet gotten to the law of cosines. So let's see what happens. A park service plans to build a bridge over a reservoir. So here is the reservoir. And here is point A. And here is point C. And they want to build a bridge over the reservoir that connects point A and point C. A and B are 2 points on the shore of the reservoir. So here's B, such that the distance AB is 14 meters. So this is 14 meters. A hat is 102 degrees. And B hat, they form a full triangle. I'm going to make this a little larger so I can fit in more. So this is 102 degrees, and B hat is 58 degrees. Notice that my triangle certainly does not look like a 102-degree angle, but that's the beautiful thing. How it's labeled is all that matters. I mean, you want to be close, and you're certainly more than welcome to draw a new triangle if you want, but you don't have to as long as you understand the labeling. So calculate the length of the bridge to the nearest meter. So this is not a sig fig problem like usual. We don't do 3 sig figs. I mean, it might be 3 sig figs, I don't know, but to the nearest meter. Of course, with a 14-meter length, chances are it's only going to be a 2-digit answer. So do we have an angle side pair? Let's see, I have 14 meters. I don't have the angle opposite it, but I can find the angle opposite it because I have 2 angles. This is 20 degrees. And we're looking for this. We're looking for a side. So sides on top, 14 over sine of 20 degrees equals the currently unknown x over sine of 58 degrees. 14 divided by sine of 20 degrees times sine of 58 degrees tells me that x is approximately 34.7, rounded to the nearest meter, 35 meters. Okay. According to the book, why do they throw this in? Because it's a practical problem. There's nothing special about this problem compared to the ones that we did earlier, but this is practical. And that's true, it is practical. It's, you know, building bridges and stuff like that is kind of important. Next example. 2 people at points A and B observe a sailboat at position C. So we have a triangle here. They were nice. They gave us a triangle. Here's point A, here's point B, here's the sailboat at point C. The distance between points A and B on the shoreline is 20 meters, so we can label that. The first observer measures A hat equals 65 degrees to the nearest, and the second observer measures B hat equals 42 degrees. Even before I read more in the problem, you have two angles, get the third. So even before I read more, bam, I get 73 degrees. They didn't technically give me this, so I'm going to change the color because I like to distinguish between what they give me and what I can actually establish. But 65 degrees, 42 degrees, 73 degrees. Find the distance from C to the shoreline. Oh, the distance from C to the shoreline. We are actually looking for this distance right here. Now, notice, first I'm going to rewrite the 73 degrees as just C hat equals 73 degrees because it kind of gets in the way a little bit. But this is very important. When they say the distance from C to the shoreline, and if you go back to the beginning of the problem, it says the distance between points A and B on the shoreline. So the bottom is the shoreline. You can reach the shoreline in many ways. You can go this way to the shoreline, or this way to the shoreline, or straight back, or this way. Or this, there's a lot of ways to reach the shoreline from part C. So what do they mean the distance from part C? Point C, they mean the shortest distance from point C, which is making a 90-degree angle with the shoreline. That is the shortest distance, because anything else would be at an angle and would be longer. So we want this right here. We want this length here. How in the world are we going to find it? Well, it turns out that knowing that C had a 73 degrees is actually irrelevant for this problem. But I do want to make sure that this 20 meters is known to be the entire thing, because now that I've split up the bottom, you might think, oh, is it 20 on the right? Is it 20 on the left? Be clear, the 20 is the entire thing. So we know that this here is 48 degrees because this is a right triangle. And this here is 25 degrees because it is a right triangle. It does add up to 73 degrees, of course, as it should. But the question is, how do we find this length? Well, if I can determine one of the three lengths of either the left triangle or the right triangle, or two of the lengths, then, one length, I can use SOHCAHTOA. For example, if I can figure out this length right here, then because the right side is a right triangle, I can use SOHCAHTOA to find this vertical. So is there a way for me to find that side? Well, let's go back to the outer triangle. Do we have a law of sine situation? And the answer is yes. First, I'm going to call this X just to give it a name. And it's a length that I'm looking for. So 20, which is the bottom length, over sine of 73 degrees is equal to X over sine of 65 degrees. That's using the outer triangle, which means, without actually taking out my calculator yet, that X is equal to 20 sine 65 degrees divided by sine of 73 degrees, which is approximately 20 sine 65 divided by sine 73. That's approximately, it's a length, so we're going to use meters, 19.0 meters, approximately. Now that I know that, now that I know X, now this is known at this point. So now if I want to use SOHCAHTOA and I want to use, let's say, the 42-degree angle, then it's the opposite that I'm looking for, and I have the hypotenuse. Opposite and hypotenuse is sine. So sine of 42 degrees equals opposite, we'll call this y over hypotenuse, which is x, which means that y is approximately 19.0 meters times sine of 42 degrees, which gives me 2 3 figs, because they didn't tell me anything else, 12.7 meters. So you see a problem like this is you can't just immediately go to the thing that you're looking for. You first have to find something else and then use that to find the thing that you're looking for. Okay, and those are, to be honest, more practical problems in the grand scheme of things, where it's not always so obvious how to go from one step to another. So let's go ahead now and talk about the next law that you use for non-right angle triangles, which is the law of cosines. Notice the law of sines used sines. Sine of A over A, sine of B over B, sine of C over C. What do you think the law of cosines is going to use? Exactly. It's going to use cosines. So what does the law of cosines say? Well, again, you have to have a triangle. A, B, C, side A, side B, side C, angle A hat, angle B hat, angle C hat. So the law of cosines, also it's in your formula book, but the law of cosines is an extension of the Pythagorean theorem. The Pythagorean theorem would say that c squared is equal to a squared plus b squared. That is the Pythagorean theorem, but it's not a right angle triangle. Because it's not a right angle triangle, you can't use the Pythagorean theorem. However, the law of cosines is an extension of the Pythagorean theorem where you subtract from a squared plus b squared to AB times the cosine of angle C. So it's like the Pythagorean theorem, and then we remove a little bit. Now be careful when I say remove, because what you can remove might be negative, which means you could be adding. Minus a negative is plus. So we subtract 2AB cosine C. Now, for right triangles, you have a hypotenuse, and we always label the hypotenuse as C. But if it's not a right triangle, there's nothing to distinguish C from either A or B. So there's actually 3 different versions of this, but they're all really the same. Doesn't matter which one you use, as long as you recognize that whichever side is by itself on the left of the equal sign, the only time that that letter appears is inside the cosine. The other 2 are always the other one. So b squared equals a squared plus c squared minus 2ac times cosine of angle B. And a squared equals b squared plus c squared minus 2bc times the cosine of angle A. It's not 3 different equations. It's the same equation 3 times, depending on how you label things. So given those, let's do an example. So you have a triangle. Now this triangle that they drew here in the book certainly looks like it's a right triangle, but they don't tell me that it's a right triangle, so don't label it. We have angle A, we have vertex A, technically vertex B and vertex C. We have 14 centimeters here, we have 7 centimeters here, and we have 12 centimeters there. That's what they give you. And it says find the angles. Now, remember what I said about the law of sines. You use the law of sines when you have an angle side pair and something else. Well, here you do not have an angle side pair because there's no angles. How are you going to have an angle side pair with no angles? So the law of cosines is a completely different property. For the law of cosines, you use it when you have 2 sides and something else. In this case, do we have 2 sides and something else? Yes, we have 2 sides and the other side. So we certainly can use the law of cosines. So which angle should we go for first? It doesn't really make a difference, but you know what? I'm curious about angle A because it looks so close to 90 degrees. They drew it that way. So I wonder what the angle actually is. So let's use the third version. A squared, 14 squared, equals b squared, 12 squared, plus c squared, 7 squared, minus 2 times b times c times the cosine of angle A. Now, it's very easy if you plug everything into your calculator at once to make a math mistake. So because order of operations, while it should be second nature to everyone, unfortunately is just not. So let's break it down. First, 14 squared is 196. 12 squared is 144. 7 squared is 49. 12 times 7 is 84. Times 2 is 168. So minus 168 cosine of a hat. 144 plus 49 is 193 minus 168 cosine of a hat. And this is where people make a silly mistake. And silly in the sense of you're in the IB, you're juniors and seniors in high school. You should not be making a mistake that is taught in 4th grade. But it's an easy mistake to make because it just seems natural. 193 minus 168. But it's not 193 minus 168. The 168 and the cosine of a hat are connected. Order of operations says multiply before subtract. So you cannot just ignore the times. What you need to do is subtract 193 on both sides. So you get 3 equals negative 168 cosine of a hat. And then divide both sides by negative 168. So you get cosine of a hat is now approximately negative 0.0179. Again, I keep all decimals on my calculator, even though I only write a few of them. Now I have cosine of a hat, but I want a hat. How do I find it? The answer is do the arc cosine. Cosine inverse of negative 0.0179. So cosine inverse of this number gives me a hat is approximately 91.0 degrees. So sure enough, it was just about 90 degrees. Their picture was fairly close. So now we have a hat. I'm going to go back to the picture and write 91.0 degrees here. So now I need B hat or C hat, but I don't need to use the law of cosines again. I could, but now that I have one angle, I can now use the law of sines. The law of sines, I need an angle side pair, which I have. So if I want angle B, for example, I want an angle, so I'll have angles on top. Sine of 91.0 degrees over 14 is approximately, because 91 degrees is only an approximation, right? My calculator actually says 91.0231933. So it's an approximation, is approximately sine of B over 12. So sine of my answer times 12 divided by 14 gives me that, sine of B hat is approximately 0.857. How do I find B hat if I have sine of B hat? Nope, that's the arc sine. So I get B hat is approximately 59.0 degrees. And oh, there's a little mistake in the book. Another one. There's so many. It's crazy. And then I go back to here and I have 59.0. Oh, if you're following along at home, the mistake is that on the top of page 59, it says A hat equals, and it really should be B hat equals. Minor mistake, easily recognized for what it is, but a mistake nonetheless. So now I have two angles. So how do I find the third? Do I want to use the law of cosines? Do I want to use the law of sines? No, because I have two of the three angles. Just go directly to, they have to add to 180. So I go back to my 91.0231933, and I add it to my 58.982081117. Remember, all decimals. And I do 180 minus that, and I get that C hat is approximately 30.0 degrees. And that's an example of using the law of cosines, then using the law of sines, and then using geometry. Let's do another example because I'm just having too much fun not to. Find the length of a lake. Oh, a little picture. Here's my lake. Should have used blue, but what could you do? There's the, oh, you know what I can do? Here's my lake. Yeah, okay, there's my lake. Okay, there's my lake. Wonderful. Find the length of a lake. So we have point here. We got a picture. It labels it as C. It labels it here as B. We want the distance between them. Given the distance is AB, so A is down here somewhere. So this distance here, A is AC is 225 meters. AB, which is this length right here, is 290 meters. And angle A hat is 72 degrees. And we will like the distance CB across the lake. Very practical problem. So the law of sines is not appropriate because I have no angle side pair. Angle missing the side missing the angle, side missing the angle. Need an angle side pair. But for the law of cosines, I just need two sides and something else. Do I have two sides and something else? I sure do. So we'll call this side here lowercase a because it's opposite angle A. And I'm going to use a squared equals b squared plus c squared minus 2 times b times c times cosine of angle A. This is even easier than the last one because we have everything on the right. Just 225 squared plus 290 squared minus 2 times 225 times 290 times cosine 2. And this gives me 94398.28223. Again, it's only approximate because even though my calculator has all of these decimals, I know that there's more. And therefore, what is A? Well, A is therefore the square. This is A squared. A is the square root of this. So take the square root of this number, and we get A is approximately to 3 sig figs, 307 meters. So another very practical problem solved using trigonometry, the law of cosines in particular. Here's another example. Towns A, B, and C form a triangle, and the triangle is drawn here, something like this. And here's town A, and here's town B, and here's town C. Side BC is 8 kilometers. BC is 8 kilometers. Side AC is 13 kilometers. And angle C hat is 50 degrees. Find A hat and B hat. So we only have one angle. And we do not have the side opposite it, so we cannot use the law of sines. But I do have two sides and something else, so I can use the law of cosines. So because I have angle C, I'm going to solve for side C, this one right here. So now, of course, they don't want side C. They want the angle. They want A hat and B hat. But unfortunately, I have to, well, I wonder if there's a more complex solution that would allow you to bypass side C. But I'm not thinking it right off the bat. And to me, if you are solving a problem and you come up with a strategy for doing it, and maybe it's not the best strategy or the fastest strategy, but it's the simplest one in your mind, just go for it. For me, I'm going to first find side C. So C squared equals A squared plus B squared minus 2AB cosine of angle C. 64 plus 169 minus 2 times 8 times 13 times cosine 50 degrees. This gives me approximately 99.3. So when I take the square root of that number, I get approximately 9.96, and it's kilometers. So now I have 9.96 kilometers is a side C. Now I have an angle side pair. Because I have an angle side pair, now I can use that angle side pair to solve, for example, A hats. You want an angle? Okay, you want an angle? Angle's on top. So sine of 50 degrees over 9.96 is approximately sine of a hat over 8. So I take sine of 50 degrees, divide it by 9.964947425. Again, even though I wrote 9.96, I use all the decimals. Multiply by 8, and this gives me that sine of a hat is approximately 0.615. So if I, oops, that's not a hat. So if I want a hat, use the arc sine of my answer. A hat is approximately 38.0 degrees. That's what my calculator gives me. Now, can that be correct? And the answer is certainly, because think about it. We know side C, which is 9.96, is opposite the 50-degree angle. So angle A, which is opposite 8, must be smaller than 50 degrees because it's a smaller length, therefore a smaller angle. So 38 degrees seems very, very reasonable. 38.0 degrees. And how do I find angle B? I don't need the law of cosine. I don't need the law of sines. Once you have 2 of the 3, so just add them together, subtract it from 180, and I get B is 92.0 degrees. Does that make sense? Now, that's not what they have here. So did I make a silly mistake, or did they make a silly mistake? Their AB is 9.96, and their sine A was 45.8 degrees. So let's just check my math. Sine 50 times 8 divided by 9.96. And the arc sine of that, nope, I got a completely different number than they did. So I'm pretty sure they're wrong again. Oh, Oxford. Too many mistakes. Okay, and now let's end today's video with doing exercise 2B. Again, as always, you should be doing these on your own and then checking the answer with mine after you do it. So, question number 1. Use the given information to find all sides and angles in each triangle. So, part A, we have A is equal to 12 centimeters. We have B is equal to 6.5 centimeters. And C is equal to 7 centimeters. Okay, can we use the law of sines? No, we don't have a side angle pair. Can we use the law of cosines? Yes, because we have 2 sides and something else. You can always make a triangle if you want. If you label A, B, and C, then angle A is opposite side A, angle B is opposite side B, and angle C is opposite side C. So which one should we solve for first? Angle A, angle B, or angle C? Let's solve for angle A, the one that's opposite the longest side, because then I know that every subsequent side must be smaller. So 12 squared equals 7 squared plus 6.5 squared minus 2 times 7 times 6.5 times cosine of a hat. So 144 equals 49 plus 6.5 squared is 42.25. 2 times 7 times 6.5, that's minus 91 cosine a hat. 49 plus 42.25, that's 144 equals 91.25 minus 91 cosine of a hat. Do 144 minus 91.25, so 52.75 is equal to negative 91 cosine of a hat. If I divide by negative 91, I get that cosine of a hat is approximately negative 0.580, so that a hat is approximately the inverse cosine of this number, which is 125, well, 3 6 figs, approximately 125 degrees. So my figure is way off because that is certainly not a 125-degree angle, but as long as I label it, I just claim that I was not taught art well, and I'm not a good artist. Now that I have one angle, it's probably best to use the law of sines. We're looking for angles, so angles on top. So sine of 125 degrees over 12 is approximately, and I'm going to go to the next largest, which is opposite 7. So sine of c hat over 7. So sine of 125 degrees, 125.4273587 divided by 12 times 7. And then do the arc sine of that. So I get that c hat is approximately 28.4 degrees. And once I have two angles, I just use geometry to find a third. I take the original 125.4273587. I add it to 28.38082585. And I do 180 minus that, and I get 26.2 degrees. So that was A. Let's do now B. For B, I'm given that A is equal to 11 millimeters. B is equal to 14 millimeters. And C is equal to 18 millimeters. So this is really the same as the last one. It's just different numbers. So here's vertex A, vertex B, vertex C, opposite A, 11 millimeters, opposite B, 14 millimeters, opposite C, 18 millimeters. Let's find C hat first because it's the largest angle because it's opposite the largest side. So 18 squared equals 11 squared plus 14 squared minus 2 times 11 times 14 times cosine of angle C. So 18 squared, that's 324 equals 121 plus, what is that, 196. 2 times 11 times 14 is 308. Cosine of C hat, 121 plus 196, so 324 equals 317 minus 308 cosine of C hat. 324 minus 317, so I get 7. Equals negative 308 cosine of C hat divided by negative 308 gives me cosine of C hat is approximately negative 0.0227. So that C hat is approximately the inverse cosine of 91.3 degrees. Now that I have one angle, we'll go to the law of sines to find the next angle, which is B, middle side. We're looking for an angle, angles on top. So sine of 91.3 degrees over 18 is approximately sine of B hat over 14. So sine of 91.30228894 times 14 divided by 18 gives me sine of B hat. So I'll take the inverse sine. And I get that B hat is approximately 51.0 degrees, which is smaller, which is good. Add that to the 91.3 degrees. Whoops. Okay. 280 minus it, and I get A hat is approximately 37.7 degrees. Biggest, middle, smallest. Good that we have confirmation. And C, I need a new color. Blue. Okay, C. We have C is equal to 22 meters. We have A hat is equal, not approximately, is equal to 25 degrees. And we have B hat is equal to 83 degrees. Ooh, we don't have an angle side pair, AA, BB, or CC, and we don't have two sides. What do we do? Well, obviously you have to get them. You have to get something. And immediately I see, because I have two angles, I can add them and subtract it from 180 to get the third angle. So 25 plus 83, subtract that from 180, gives me that C hat is equal to 72 degrees. And now I see that I do have an angle side pair and something else. So I'm going to use the law of sines. Even though this is section 2B, they don't tell me specifically what to use. And to be honest, I can't even use the law of cosines because I don't have two sides. I have to use the law of sines. So we're looking for the other two sides. So A over sine of 25 degrees equals B over sine of 83 degrees equals C over sine of 72 degrees. Okay, so 22 divided by sine of 72 times sine of 25. A is approximately 9.78. What are my units? Meters. And if I go back to 22 over sine 72 degrees, and I multiply by sine of 83 degrees, I see that B is approximately 23.0 meters. And very strange that this would be in the section on the law of cosines when it is a straight up law of sines problem. Okay, question 2. It says use the given information to find all sides and angles in each triangle. So here's part A. And we got it. Oh, well, it doesn't really make a difference as long as we label it. So they have two sides, 70 millimeters and 84 millimeters. And they have the angle opposite the 84 millimeters. It says use the given information to find all sides and angles in each triangle. So in this case, we actually have a choice. We get to use the law of cosines because we have two sides and something else. And we get to use the law of sines because we have an angle side pair and something else. Personally, I think the law of sines is a little bit easier, so we're going to use that one. So we're looking for the angle. We're looking for the angle opposite 70. So sine of 52 degrees over 84 units suppressed equals sine of, we've got to give this guy a name. They don't in the figure, so we'll call it A. So sine of A hat over 70. So sine of 52 degrees divided by 84 times 70. So this gives me that sine of A hat is approximately 0.657. So that A hat is approximately, by taking the inverse sine, 41.0 degrees. Does that seem reasonable that it should be 41.0 degrees? Well, it's got to be less than 52 because it's opposite a smaller side. So 41 degrees seems extremely reasonable. And once I have two angles, I can add this to the original 52 and subtract it from the 180 and gives me my third angle, which again we'll call B. So B hat is approximately 87.0 degrees. So now we have, and that's of course going to tell us that the third side must be the largest. So how do I find the third side? How do I find side B? Well, nothing wrong with the law of sines again. This time we're looking for a side. So we're going to have the side on top. So let's use 84 over sine of 52 degrees is approximately the currently unknown B over sine of 87 degrees. Of course, not really 87. It's 86.95317.261 on my calculator. So 84 divided by sine of 52 degrees times sine of that answer tells me that B is approximately 106 millimeters, which again is consistent. Biggest angle, biggest side. Okay, it's always nice to throw in those little mental checks to make sure that we don't do silly mistakes. Next, B, new color. Let's use that one. Okay, B. So again, we have this triangle here. And this angle here is given as 66 degrees. This angle here is given as 48 degrees. And this side here is given as 14 centimeters. And it says use the given information to find all sides and all angles. Well, I do not have two sides and something else, so I cannot use the law of cosines, but I do have an angle side pair and something else. So I can use the law of sines. If I label this as side A, I'm looking for a side, so 14 over sine of 48 degrees equals A over sine of 66 degrees. 14 divided by sine 48 times sine 66 tells me that A is approximately 17.2, what are my units? Centimeters. Does that seem reasonable? Well, it's a bigger angle than 48, so to be a bigger side, and it is. So that does seem reasonable. So now we have two sides. Of course, I should have done this right off the bat. You have two angles, get the third. So 66 plus 48 is 114, and if I do 180 minus 14, that gives me another 66-degree angle. And that's wonderful, because that tells me that this triangle is isosceles, and that the sides next to the 66-degree angles are equal. So without doing any more work, I know that this one is also 17.2 centimeters. So that was a nice coincidence and probably the intent of the problem. Remember, trigonometry is great, law of sines, law of cosines, but always be on the lookout for where ideas from geometry can save you time and energy. So part C, another triangle. Oh, this one has letters in it. How annoying is that? This is 3x as an angle. This is 4x as an angle. This is 2x as an angle. And this is 25 meters. So we actually only have one side. We don't have any angle. And we don't have the other two sides. So this one is, in terms of what we have to do, the longest problem. We have 5 things to find versus usually only 3. So how do we do it? Because we can't use the law of sines or the law of cosines. So we don't have an angle side pair. We don't have two sides. But what I do have is expressions for the 3 angles. And I do know that the 3 angles have to add to 180 degrees. So 2x, 3x, and 4x, which is a total of 9x, must add to 180 degrees, which means x must be 20 degrees. So which means this angle here being 2x is 40 degrees. This angle here being 3x is 60 degrees. And this angle here being 4x is 80 degrees. 80, 60, 40, that does in fact form a 180-degree triangle. Wonderful. So now I have an angle side pair and something else. So I do want to use the law of sines. I'm looking for sides on top. Call this A, call this B. So 25 over sine of 80 degrees equals A over sine of 40 degrees equals B over sine of 60 degrees. 25 divided by sine 80 times sine 40. This tells me that A is approximately 16.3 units or meters. And if I go back to 25 over sine 80 and I multiply by sine of 60, B is approximately 22.0 meters. Does this seem reasonable? Smallest angle is 40. Smallest side is opposite it. Next smallest is 60. 22 is opposite it. And 80 degrees is the next is the largest. And 25 being the largest is opposite it. That all is consistent. So that's wonderful. Why can I not draw a straight line? Okay. All right. Question number 3. Let's do this one. Question number 3. A surveyor has to determine the distance between points A and B that lie on opposite banks of a river. So here's the river. And here is point A on this side. And here's point B on this side. I'm assuming they're right across from each other. Perhaps not. If we see within the problem that it's not, or there's additional information, I might have to go back and change my picture. But for now, the surveyor has to determine the distance between points A and B that lie on opposite banks of a river. Another point C is 450 meters from A on the same side of the river, such that BAC is 45 degrees and okay, so I certainly am not drawing the picture right. So let's start again and ignore the river for a second. It says a surveyor wants to determine the distance between points A and B that lie on opposite banks of a river. So, okay, so here's one side of the river, and here's the other side of the river. And it looks like they are not directly opposite each other. So we'll put this one here. So here's A and here's B. Another point C is 450, actually, let's call this one down here A, and this one here C. BAC is 45 degrees. So if I make this angle here 45 degrees, it says point C is 450 meters from A on the same side. Okay, I'm thinking I get this now. So here's C. Okay, let's try this again. A surveyor has to determine the distance between points A and B that lie on opposite banks of a river. Another point C is 450 meters from A on the same side of the river, such that angle BAC is 45 degrees, and ACB is 55 degrees. Okay, so that matches what I'm told. So sometimes this illustrates, sometimes as you're reading a problem, you got to draw a picture. You should draw a picture to illustrate it. Your first impression might not be correct. What do? You just start over. Nothing wrong with that. Find the distance from A to B to the nearest meter. We are looking for this side here, A to B to the nearest meter. Well, let's take a look. I don't have two sides. I cannot use the law of cosines. I do not have an angle side pair. I cannot use the law of sine. So I have to go to geometry. I have two angles, 55 and 45, which adds to 100, which means the last angle is 80 degrees. And now that I have that angle, now I do have an angle side pair. So I'm looking for a side, 450 over a sine of 80 degrees equals the currently unknown x over sine of 55 degrees. So 450 divided by sine 80 times sine 55. And that tells me to the nearest meter that x is approximately 374 meters. Does that seem reasonable? Well, it's less than 450. And 450 is the side opposite the biggest angle. So if I got something more than 450, I might start worrying. I would start worrying. Now I don't have to. Question number 4. It says, a hiker leaves camp. So here's camp. A hiker leaves camp and walks 5 kilometers on a bearing of 58 degrees. So for bearing, we always draw one line north, and then we tilt 58 degrees. So he's walking this way, and he goes a distance to here of 5 kilometers. 5 kilometers at a bearing of 58 degrees. He stops for a break, then continues walking for another 8 kilometers on a bearing of 103 degrees. So we draw a new straight up north, and now a bearing of 103 degrees, which would be something like this. And he goes a greater distance this time. This is 103 degrees, and he goes 8 kilometers. He stops again before heading straight back. So straight back is right back that way. Find the distance back to camp from the second stop. So we're looking for x. So I have 2 sides of my triangle, but I don't have something else. If I can find something else, then I can use the law of cosines. I also do not have a angle side pair. So the question is, how do I use what I'm given to figure out the answer? So what we're going to do is throw in. So first, you should definitely pause this and attempt to do it yourself. This one is not straightforward. Probably the hardest question yet, but you should certainly pause and attempt to do it. And so remember, in the absence of law of sines or law of cosines, you have to revert to geometry. What are some of our geometric concepts? There's the sum of the angles adds to 180 degrees. Can't use that here. There's the fact that the isosceles triangle, two sides are the same, or equilateral triangle, three sides are the same, can't use here. But one of the big ones about geometry is what you do when you have parallel lines. And in this case, we have two parallel lines. We have the original bearing, which creates that line, and the new bearing, which creates that line. And these are parallel because they're pointing north. So if you remember your geometry, when you have parallel lines, and then you have this transversal, this segment or ray or line that cuts across them, it creates what are called alternate interior angles. That if this one here is 58 degrees, then this one here is also 58 degrees. Hopefully that rings a bell. On the other side, we have 103 degrees, which means we have 77 degrees. If you take 58 plus 77, that tells you that this whole angle here is 135 degrees. And that information then gives you an angle. And I can now use the law of cosines because I have two sides and something else. X squared equals 5 squared plus 8 squared minus 2 times 5 times 8 times cosine of 135 degrees. 25, 64, 80 times cosine of 135 degrees. So 25 plus 64 is 89 minus 80 cosine of 135 degrees. 89 minus 80 cosine 135 gives me approximately 146. Again, I'm only writing 3 digits, but there's a lot more on my calculator. But either way, the square root of this number is 12.1, and my units are kilometers. Does that seem reasonable? Well, I went 5 and 8, which is 13. Had I gone in a straight line 13, then it would take me 13 to come back. I went off on a detour, so it's actually going to be less than 13. 12.1, certainly less than 13, and is very reasonable, so I don't question it. And I have the answer to that question. 2 more to go. Question 5. It says, the straight line distance between two cities A and B is 223 kilometers. So here's A, straight line distance to B is 223 kilometers. The straight line distance between A and C is 152 kilometers. So A and C, I don't know which direction it is yet. I'll just draw it here, and if I have to change it and fix it, I will. But A and C is 152 kilometers, and the straight line distance between B and C is 285 kilometers. Find the angles between each of the 3 cities. Okay, so we're looking for A hat, we're looking for B hat, we're looking for C hat. I don't have an angle side pair, can't use the law of sines, but I do have 2 sides and something else, so I can certainly use the law of cosines. We're going to find A first because it's opposite to the longest side. So 285 squared, A squared equals 223 squared plus 152 squared minus 2 times 223 times 152 times cosine of the currently unknown angle A. So 285 squared, that's 81,225 equals 223 squared, that's 49,729 plus 152 squared is 23,104 minus 2 times 223 times 152, 67,792 cosine of A hat. So 49,729 plus that. So I have 81,225 equals 72,833 minus 67792 cosine of A hat. 81,225 minus 72,833. So I have 83,92 equals negative 67792 cosine of A hat divided by negative 67792. So cosine of A hat is approximately negative 0.124. And therefore A hat take the arc, cosine is approximately 97.1 degrees. So now we have the biggest angle. Next biggest will be C. So we're going to use the law of sine. Now that we have an angle side pair and something else, I'm looking for an angle, so angle's on top. So sine of 97.1 degrees over 285 is approximately sine of angle C over 223, sine of what I just got divided by 285 times 223, take the arc sine of that, and I get that C hat is approximately 50.9 degrees. And now that I have two angles, geometry, the first one plus that one, 180 minus the sum, gives me 32.0 degrees for angle B. And our last question of this exercise, question number 6. To find the third side of triangle ABC, so we have some triangle ABC. I'm going to call this A, call this B, call this C, with AB is 40 centimeters, and BC is 25 centimeters, and BAC, angle BAC, that's this one down here, is 35 degrees. Valina and Christian offer the following suggestions. Christian suggested use the cosine rule as you are given two sides and an angle. Well, two sides and something else. Way to go, Christian. Valina suggested use the sine rule as you are given two sides and an angle opposite to one of them. You have an angle side pair and something else. Way to go, Valina. State whose method is correct and justify your statement, hence solve the triangle. Well, they're both correct. You can use either one you want because, oh, actually, I apologize. No, I was right. Never mind. So either one is correct. You can use the cosine rule, two angles, two sides and something else, and you are given the sine rule, an angle side pair and something else. I think the law of sines is just a little bit easier. So since we have the pair right there, let's find angle C. So we're looking for an angle. Sine of 35 degrees over 25 units suppressed equals sine of the currently unknown angle C over 40. Sine of 35 divided by 25 times 40. And then the inverse sine tells me that C hat is approximately 66.6 degrees, which is bigger than 35 degrees. So the side should be bigger than 25, 40 it is. That seems reasonable. Once I have A and C, I can add them to get B, 35 plus that angle, subtract it from 180. That tells me that angle B is approximately 78.4 degrees, which is the biggest of the three angles, which means that the side opposite it should be the longest side. Let's check. 25 over sine of 35 degrees is approximately b over sine of 78.4 degrees. 25 divided by sine of 35 times sine of 78.4. And this tells me that b is approximately 42.7 centimeters. It's the longest side, biggest angle, and we're happy. So that takes us to the end of section 2. Exercise 2b, section 2.1. I have to admit, a little disappointed that there were no problems that illustrated the possibility of multiple solutions to triangles. It's possible that the IB does not cover them, although I'm pretty sure it should. So a little disappointing. Maybe we'll see some in the chapter review and the exercises at the end of the chapter. If not, we will certainly go over them in class. But either way, this takes us to the end of 2.1. So hopefully you did well. If you have any questions, feel free to ask, and I will see you next time in section 2.2. Bye.